Hello, everyone, and welcome back to the 2023 Hack Summit. I'm here with Sriram Kannan, who's the co-founder of eigenLayer, and he's going to be giving us his vision for the future of restaking. And it's an incredible new technology breakthrough that he's developed in academia that he's now commercializing. And we are very proud to have him here and very lucky to have his attention. So thank you, Sriram.
Thank you so much, Ed. My pleasure to be here. Yeah.
So Sriram is going to, I believe, be giving a presentation, right? And then at the end, we'll take some audience questions. Does that sound good to everyone? Great. Awesome. So Sriram, go ahead and share your screen and take it away. And by the way, before you start, I'd love for you just to give a very brief overview of yourself and your background, just so the audience can get to know you.
Yeah, thank you so much, Ed. I'm Sriram. I founder of eigenLayer, which is this project trying to reuse trust from Ethereum. Broadly, before that, and even now, actually, I've been on leave from the University of Washington, Seattle, where I run the UW Blockchain Research Lab. We've been working on how to develop new consensus protocols, scalability primitives, game theory associated with blockchains. So it's my pleasure to be here.
Thank you, Sriram.
Awesome. So let's dive into today's topic. I had promised, Ed, I'll talk a little bit about how we can build new and interesting things on top of the platform that we're building called eigenLayer. Particularly, I'm going to talk around the first service that we have built on top of eigenLayer called eigenDA. How you can use it to build new, cool, and interesting things. Firstly, I want to always thank our team, which I'm just the face here trying to represent what we are doing, but there is a big group of people who are actually building all these things. Okay, so let's zoom out and take a look at what blockchain applications are kind of interesting and where we are in this space today. Before that, I want to kind of root it in two kinds of metrics that I think we need to think about, which is how much value per bit. Like when you think about how to think about the topography of applications, you think of two metrics. One is value per bit, which is, if you're doing, for example, a financial transaction, you may be transacting $100. And, to do this, you may need a 200 byte transaction. So it's you're transacting $100 per 200 bits, right? So that's roughly a unit of how valuable each bit of information is. So that's value per bit, one dimension. Another dimension is throughput, what is the rate at which you're generating bits, right? And you can kind of categorize applications in this two-dimensional graph. On the one axis, you have value per bit, how valuable each bit is that you're transacting on this blockchain. And the other axis is throughput, how many bits per second, for example, are you transacting? What we see is pretty much a large class of applications that we see today, decentralized finance, for example, all transact large amounts of value per unit bit, but usually don't have that high throughput. But there is a kind of category of very interesting new applications that are emerging where the value per bit is not that high. Right? For example, any one tweet may be 200 bits, but it's not necessarily, each tweet is not worth $100. So you have high throughput, but low value per bit. And blockchains today have been basically only able to serve, applications which have high value per bit and low throughput. And this is due to two reasons, because value per bit is fundamentally bounded by the cost per bit. How much cost does it actually take to commit to a given bit? And if the cost per bit is, the cost basis inside the blockchain is high, you cannot transact much more value than that. And so essentially and then the throughput of blockchains, of course, also low. So you are essentially focusing on a small category of possible applications. But there's a whole other category of applications which are very, very high throughput, but value per bit is low, but the total value, which is the product of value per bit and throughput, may still be very high. So that's why I kind of draw this curve, that's xy equals constant. That's the product of these two is the same. And you could be very much profitable building these things if only you could reduce the cost per bit. Okay, let's look at what the cost per bit, is contributed by. Ironically, the dominant cost per bit in any of the existing blockchains today is capital cost, which is how much does it take for, because these blockchains usually are protected by mechanisms like proof of stake. You need a certain amount of staking to happen. And since you want a certain amount of stake in order to have security, you take a certain amount of capital cost. You also have other important drivers to cost, which is things like operating cost. How do you make sure that actually running and upkeep of the network are low cost? And finally, how do you make sure that there is another type of cost is congestion cost, which is when too many people are trying to use the same common resources, there's an externality induced in terms of congestion to others, and people have to pay for it. Essentially, blockchains have all these three costs operating. And when you want to determine where the cost per bit is dominating, like I said, there's a lot of the fundamentals, basically the capital cost. And one high-level primitive and message that I want to convey here is having a common pool of capital secure many, many, many applications reduces the capital cost per bit. So shared security reduces the capital costs per bit. So what does shared security mean? You may have a common blockchain and many applications are using these blockchain. You may have a common blockchain on which many rollups are actually absorbing security from this common blockchain. You may have something like eigenLayer. eigenLayer is a mechanism where Ethereum stakers offer their staking and security and opt in to new primitives to share their security. Shared security fundamentally reduces capital cost per bit. So this is one mechanism by which we can mitigate or reduce the amount of capital cost per bit that we actually suffer. The second dimension is operating costs. And what do we mean by operating costs? You have to actually have n nodes in the network. All of them run a common protocol and then share, or private consensus or whatever needs to be done. And by building better technology, better distributed systems, you can actually reduce the operating costs. Like, for example, existing distributed systems, existing blockchains, all require every unit of bit to be returned to every node. So this is one kind of like an operating expense. And finally, you have congestion costs. And congestion is an externality created to somebody else, and you have to pay for it. And one way to reduce congestion cost is by increasing the amount of shared throughput. Like if we had a very, very high performance blockchain, then basically you're not going to have that much congestion. So essentially, by controlling all these three costs, you can actually reduce the cost per bit massively. And why is this interesting? It's interesting because now you can start approaching a massive category of applications that were simply inaccessible in the underlying economics of today's blockchains. So that's the first high level. And I think, all of this sets up the context for why we think like architectures such as rollups are actually ideal for building applications like this. Okay, so what happens in a rollup? You have an idealization of an entity called a sequencer. A sequencer collects transactions from the nodes, and then it's basically writing transactions into a layer called the data availability layer. What happens in the data availability layer is you're publishing the inputs to the computation or outputs to the computation so that the data is available publicly so that anybody else who wants to replicate that computation and check it can actually do it, or wants to continue the execution beyond you, they can actually do it. So that's the data availability layer. You also have to write whether if you execute these units of data, you actually get this particular output. And usually you write a proof, which is called a fraud or a validity proof, to then communicate to what we call a settlement layer. And in the settlement layer, you're basically writing a proof that you've actually done the computation correctly. And what this does is essentially offload the computational hardness, like whatever computation we need and memory we need, doesn't have to be done on this bigger blockchain. You just go out and do it on your own, like single node, and just publish all of this to a broader blockchain. Okay, but today the dominant cost of rollups is actually writing data to to Ethereum. So this is the dominant cost. And so a natural question is, can we actually reduce it? Okay, so we can think about like what properties we want from a data availability layer. So what is the data availability layer? Think of it as a place where a rollup or any other system can publish inputs or outputs to its computation. So if you publish it in public, everybody knows it, then essentially other people can take it up and continue running that system. So that's the core idea. Okay, let's see what properties we need from a TA layer for it to be actually like really helpful. So the first property is hyperscale. What do I mean by hyperscale? Okay, so if we focus on a layer whose only duty is to publish data, you come to this world where you're asking, what is the rate at which I can write data into this layer? One thing we're used to as developers is thinking about, how much bandwidth, for example, your like 5G phone has. So you measure this in things like bits per second. So you can ask if there are n nodes in the system, and when I'm talking about nodes, think of the nodes that actually form the blockchain. These n nodes, there are n nodes in this blockchain, and you ask like how much bandwidth does each node have? If each node has bandwidth C, and somehow if you can create a data layer, a publication layer, where the net bandwidth is actually increases with n, it's n times C, let's say, then it'll be really amazing. But you can't really get exactly n times C in even an ideal universe, because you want to be tolerant to at least half the nodes being malicious. So this is a standard model in blockchains. You want to build systems which are resilient to a lot of nodes being malicious. Even if half the nodes are malicious, you still have the remaining good nodes, which is n times C by 2. If you did know which of those are actually the good nodes, what you could do is you could just go and find those nodes and ask those nodes only to like store the data. And since you know already they're good nodes, you're going to be fine. But the problem is you don't know which is good, which is bad, and who's going to turn bad later. And you still want this kind of a scaling. We call it hyperscaling because it is the most scaling that you can get, even if you were in a completely trusted environment. Okay, so that's why we're calling it hyperscale. You can think of it as horizontal scaling, but it's even sharper than horizontal scaling. Okay, so the other property which you absolutely need, which is what we just set everything up for, is cost. Like if we're talking about the cost per bit, then the question is, in a normal system, pretty much all blockchains today, you have n nodes in the blockchain, and to write any unit of data into these n nodes, you actually have to have each of the n nodes download and store it. So the cost structure of such a blockchain is basically n nodes downloading and storing this data. And this can be really expensive, right? And we want systems where n is really large. We want, tens of thousands of nodes, for example, on Ethereum. And if tens of thousands of nodes have to download and store every unit of data, you're talking about a very, very expensive system. So can you somehow reduce it as to maybe it's like only a couple of nodes are downloading and storing the data? That would be really cool. So that is what I call low cost. You also want to think about like, what are the fundamental latency properties you want from a data availability layer? If you had a single server, right? So all of these are basically like a wish list. Thinking of, suppose you had a cloud system, how would that system look? And can I kind of ask for something similar? So if you had a cloud system, you just, ping your Amazon Elastic block storage, right? And then like you get a ping back. So it's 2 times the latency. You send something, it goes to Amazon, Amazon sends a return back. But of course, we don't want to write anything on Amazon. We're talking about, can we mimic such low latency behavior from this system? Okay. The next thing that you want is, we're building blockchains because we want these systems to be verifiable from anybody who's not even participating in the consensus in the system. So a node or a wallet from somewhere should be able to do like a small amount of queries and be able to figure out if the system's functioning or not. And finally, you want this layer to be highly customizable. Like you should be able to tweak the parameters. You should be able to change the various things. Like, I want to pay in a different token. I want to use a different kind of a code. I want to use a different staking modality and all of these things. And so main claim is we have a data availability layer built on top of eigenlayer, which actually achieves all these properties. This data availability layer is called eigenDA. EigenDA is designed to actually be hyperscale, low cost, low latency, verifiable, and customizable. Okay, so before we get to all of this, I want to just say that briefly give a quick overview of what is eigenlayer. Eigenlayer is a mechanism by which Ethereum stakers opt in and run any other protocol that they want to run. And so, because the root of trust in Ethereum is coming from staking, Ethereum stakers can opt in and choose to download other systems and services and actually run them. And that's what we do. So eigenDA is a system built on top of eigenlayer. So eigenDA is a system built on top of eigenlayer where we can actually achieve all these properties. Basically, this is the Ethereum stakers which opt in and run this eigenDA. And if you run eigenDA, you can actually get all these properties. The core idea, I think, I don't want to get into all the details, but the core idea, I just want to iterate here, is that, it's based on, if you're running, for example, a rollup sequencer, you take the data that you want to commit to this eigenDA. What you do is you have to actually take this data and then break it up into small chunks and then perform erasure coding on these chunks. Erasure coding is a mechanism by which you create new chunks where even if some fraction of the chunks are missing, you could still reconstruct all the data. Do an erasure coding, and then you use KZG polynomial commitments, which is the underlying technology that, the simplest core of zero knowledge proofs. And so you take these two things and then do erasure coding plus KZG polynomial commitments, you can actually build a system where each of these nodes only download if you had a gigabyte file and there are 2000 nodes, each one only downloads like a 1 megabyte file chunk. But you have the property that even if half the nodes go away, you can still decode all the data. And they all need to check only some very simple proof that the chunk that they received is related to the chunk that was claimed. And that's what the KZG commitment does. Okay, so this can actually very significantly scale the system. And to give you some example, we are already running at 10 megabytes per second. That is 80 megabits per second on our testnet. And we're able to do this while each node only has very, very limited bandwidth requirements. Each node has only 0.2 megabytes per second bandwidth requirement. This is very different compared to where Ethereum is today. For example, you can write 83 kilobytes per second to Ethereum, and the node bandwidth requirement on Ethereum is 2 megabytes per second. This is not unique to Ethereum. Pretty much any blockchain that exists today all have exactly this kind of a trade-off. Okay, so that's so by the way, I want to be very clear. We have actually built this on top of the technology pioneered by the Ethereum Foundation researchers called danksharding. You can think of eigenDA as a kind of an opt-in version of danksharding, which is built on a slightly different systems architecture, but uses exactly the same underlying polynomial cryptography. Okay, so that is eigenDA, and it satisfies all these properties. I won't be able to go into why, but I want to just touch upon a couple of things. What it means for builders like several of you here who might be able to build on top of eigenDA. So eigenDA transforms rollup economics. Why? If you want to build a rollup, you have to think about what your cost structure is and how it compares to being your own L1. Today, rollup's dominant cost, like I mentioned in the beginning, is data availability, which means you have to find a place to write data securely and have this data be published. And not only that, the data availability cost is high, the data availability cost is uncertain. And it's uncertain because, when you're a rollup, I'm comparing this to being your own chain, go build a Cosmos SDK for yourself. You know how much the data availability cost is because your system is the only thing that is actually running it. Whereas if you go run on top of Ethereum or any other system, the problem is you're sharing a common data availability layer, which means your DA cost is uncertain. And finally, Unlike an L1, where there may be all these costs, but usually they have their own token and you inflate your own token to pay off the validator nodes, rollups need to pay upfront costs. Like, for example, if you go use Ethereum DA, you're paying out ETH and it's hard cash that you need to have. So eigenDA can completely transform all these dimensions of economics. DA cost is very low, and it's very low because eigenDA is designed to have very, very low cost structure. There's no capital cost. You're sharing all staking with Ethereum, so there's no capital cost. The operational cost, like I mentioned, is every node does not download all the data. Every node downloads only like 1/n of the data, where the n is the number of nodes. So it's really low, and throughput is very high. So what this means is eigenDA also has a unique economic feature called long-term data availability reservation. So you can come and say, hey, I'm building this game rollup. I need as much data availability as all of Ethereum just for myself. And you can reserve this on eigenDA. And if you come and reserve like something like this on eigenDA, you have cost certainty. You don't have cost uncertainty, you have cost certainty. And you could also, depending on what the token is and whether Ethereum stakers are okay with it, you can also pay DA fees in your own native token. So essentially, you get the benefits of being your own L1 without the cost of being your own L1. The cost of being your own L1 is you have to have a certain amount of capital stake to actually participate and validate your systems, and that's completely taken out. So that's how eigenDA actually transforms the rollup economics. I just want to highlight how easy it is to build a rollup like this. Once we are on a public testnet, right? I mentioned eigenDA is on a testnet. It's on a private testnet right now, but when we go on a public testnet, we can start playing with this quite a bit more. So if you think about what dimensions of security are there, you have validity, which is is your transaction right? You have reorg resistance. You want to make sure that your chain or rollup cannot reorg. You cannot say this is the rollup chain and then later say that is the rollup chain. Data availability, which we've been talking about. You also have dimensions of things like censorship resistance. Is your transaction, can it be censored? And then finally, I want to say there's a dimension called ledger growth, which is the idea that your rollup chain keeps growing. And if you're doing this on Ethereum, you do everything. All of these are kind of written out of Ethereum. Your reorg resistance comes from Ethereum because you're looking at the Ethereum ordering. Ethereum, you write data to Ethereum, and then you get the Ethereum DA. Censorship resistance accrues to your rollup because you have a mode by which you say, if you write a transaction to Ethereum, you have to include it in your rollup. So it's called force inclusion. And finally, if you had a sequencer, like I mentioned, which is writing data to Ethereum, you should have a protocol on Ethereum for rotating the sequencers. But the most complex aspect of building a rollup today is actually the first step, which is how do you determine your state is valid? When you update the state, when the sequencer updates the state, how does Ethereum know it's valid? You have to write either a fraud proof or a succinct validity proof, colloquially referred to as a zero knowledge proof, while it really doesn't have any zero knowledge requirements. Okay, so you have fraud or validity proofs. This is actually where everybody is one of the most complex portions of actually building a rollup. What if you said, I don't want it? I don't want to write this validity proof. Okay, so this was actually an idea introduced in the Celestia community called sovereign rollups. I'm calling this eigen rollup here because I'm going to use some specific aspects. The idea is, firstly, you do not have any validity proof written on Ethereum. You use the Ethereum ordering. You use, instead of Ethereum, you use eigenDA because you have all the advantages that I mentioned before. You use censorship resistance from Ethereum, and you have some sequencer rotation protocol. So what you can do with the eigen rollup is you've kind of given up one thing, which is the Ethereum does not know whether your state is valid, but you get all the other benefits. And if you had this, I'm just repeating that here, and if you had a kind of a rollup full node, here's the most important thing, can locally validate whether the state is correct or not. The rest of the things are all inherited from Ethereum, but the most important thing is the rollup node locally knows whether the state is valid or not. And because the rollup node knows whether the state is valid or not, you still get pretty much all aspects of safety and liveness from Ethereum, but you don't have to go write your validity. So here is a kind of summary of a rollup, a sovereign rollup or an eigen rollup designed like this. you can start building very interesting things like new virtual machines. You can inherit safety and liveness from Ethereum and EigenLayer for running full nodes. You can have very low cost and very high throughput. It's actually very easy to build and deploy because you're not actually fiddling with all the other complexity of validity or fraud proofs. The downside is that there is no safe bridge to Ethereum. And I think this is not a big deal because if you go build your own L1, also there is no default safe bridge to Ethereum. So what you need is, so the mitigation is if actually what you're building is, for example, something like a game, or if it is something like, Lens protocol, which is a decentralized social network, or, these kind of things where a lot of assets are primarily L2 native, they can actually inherit full safety of the system. An example of this would be like, for example, you create a rollup where you have native game assets, but also you have like a stablecoin like USDC launch on that particular rollup. You can actually inherit a lot of aspects of safety and liveness from Ethereum while sustaining a high rate of innovation. So with that, I think I'll stop this presentation and look forward to taking questions. Here's our website and our Twitter handle, so please follow, and a lot of new announcements coming up. There's also a lot of open positions for many of the builders, so please ping us.
Thank you, Sriram. That was a great presentation. Very, very helpful and educational. Let me go ahead and move you back on stage here so that people can see you. Great. So a few questions. Is the future one where all the stake that's using to secure these protocols is restaked? Is that the economic eventual outcome here, just because of the potential economic value that you get from restaking? What do you think?
Yeah, I mean, I think, we need, basically what I think will happen is if there is one unified layer on which all of the state can be managed. I think this is very, very important. It's not, what we're propounding is not that, oh, you go restake on EigenLayer and then you go restake somewhere else and somewhere else. You need one place in which all the state is tracked so that if you're slashed on one chain, the other chains know. So you need this coordination mechanism, which allows you to kind of know exactly how much security has been given to each layer. So for example, if there are multiple applications running on a common layer, each of these applications may be able to have unique attributable amounts of insurance. So if things get slashed, then rollup 1 will get at least this much insurance return from the slashed bonds. And these kind of attributable security are very, very important in order to actually have safe restaking, which is also why we think this is not any kind of financial leverage. This is just a mechanism to coordinate many systems to share a common security pool. What we do think is something like Ethereum is the natural place for this because you already have a lot of both value as well as developer attention. So we can actually cultivate that through EigenLayer.
Makes sense. And does restaking introduce any weaknesses into the security models for chains that choose to take advantage of restaking?
Yeah, so this is where I was like briefly mentioning about this insurance mechanism, where actually, the thing with restaking is you have this common pool of security and everybody's sharing it. But what is my attributable amount of security? That is what you're losing by actually going to a restake model, right? Like thousands of chains are all sharing, let's say, $100 billion security. It's different from each chain has like $100 million security, right? So the way we mitigate that on EigenLayer is by actually creating unique attributable assurances to each row, each system that is built on top of EigenLayer. If there is $100 billion total staking available, there is a potential to take out insurance bonds which are specific to each service. And we will not overwrite insurance, which basically means if this total $100 billion, total amount of insurance is less than $100 billion, but it's just shared. So you can both get attributable security, but also you get pooled security, which means to attack any one service, you need to still attack the $100 billion. You can get best of worlds in this kind of a mechanism.
And last question is, how can the programmers in the audience get involved with EigenLayer? Do you have any recommendations for them, courses or ideas for things they could be working on to get started?
Yes, I think the ways to get involved. What we're going to do is in the coming weeks have a lot of public-facing contracts and other things so that people can start understanding the eigenlayer system and start building on top of it. Particularly, some of the most exciting things to be built on top of eigenlayer are things that exploit this permissionless innovation to go build, let's say, new virtual machines. Can I build a WASM rollup on top of Ethereum today? Can I build a MongoDB on top of Ethereum today? Can I build a machine learning virtual machine for Ethereum? So there is a whole space of innovation in the on top to be built on top of eigenlayer. There's also fundamental infrastructure services like building new bridges, building new oracles, building new data availability protocols, building new decentralized sequencing protocols, all of these things. So there's a lot of surface area here that we're very excited about.
That's great. And then we had one question from the audience. When you say that stakers opt in, what is that opt-in process? That was the question from the audience.
There are two types of restaking, which is basically one is called liquid restaking. If you had a liquid staking token, you can just take the liquid staking token and then deposit it into eigenlayer. So that is an opt-in. You have the liquid staking token. You are depositing it. Another way, which is the more fundamental or the more powerful way, is native restaking. You stake in Ethereum, and you stake in Ethereum contracts. Normally, you will hold the withdrawal powers. What you do is you set the withdrawal credentials to the eigenlayer contracts. In the eigenlayer contracts, you set the withdrawal credential to yourself. So you're adding like one hop in the withdrawal. And what it does is give the eigenlayer contracts the power to withdraw your funds if you misbehave, and a certain provable portion of the funds can be slashed if you misbehave on eigenlayer. So that's exactly what it means by opting in, is basically either giving withdrawal credentials to eigenlayer and then setting withdrawals for yourself on eigenlayer, or just taking a liquid staking token and then opting in.
Great, thank you, Sriram. I think we're just about out of time. Thank you so much for educating us today. It was really exciting to hear your vision for eigenDA and eigenlayer, and we're excited to see where it goes in the coming months. So very optimistic for what you're building, and thank you for sharing with us today.
Thank you so much, Ed. This is always a pleasure to have the opportunity to talk to you, and today to the audience here. Thank you so much.
Thanks, Sriram. All right, everyone, we'll be back. The next session is going to be a DAO panel to learn all about decentralized autonomous organizations and how they are governed and best practices for running a DAO. So I think it'll be really fun, and we're going to have some great panelists. So we'll be right back with that panel. So stay tuned.